in this session we are going to discuss about the solutions of computer network questions in GATE 2022 examination. So look at the question statement. This is the first question we have. Look at that question statement. Consider the data transfer using the TCP over a 1 Gbps link. Assuming that the maximum segment lifetime MSL is set to 60 seconds, the minimum number of bits required for the sequence number field of the TCP header to prevent the sequence number space from wrapping around during the MSL is. So it is indirectly asking about that wraparound time concept only. This question is based on that wraparound time concept only. So the same procedure we are going to apply here. Have a look. So first, if you consider bandwidth. What is the given bandwidth here? 1 Gbps, right? 1 Gbps. And it is in terms of bits. So we need to convert this into bytes. So means that 2 to the power of 30 by 8 bytes per second. Okay. So what is the meaning of this particular 1 Gbps here? First of all, understand this. What is the meaning of this particular 1 Gbps? It is mentioned that within 1 second or else per second 2 to the power of 30 number of bits can be transferred. Okay, but we are converting this 2 to the power of 30 bits into bytes. So within 1 second we are able to convert 2 to the power of 30 bytes. So how it is? By 8. So within 1 second these number of bytes can be generated. So why we are converting these bits into bytes? Because this TCP is a byte oriented protocol, means it is assigning the sequence number to each and every byte of the segment. So that is why we are converting these bits into the bytes here. So within 1 second we have 2 to the power of 30 by 8 number of bytes, means that within 1 second we have 2 to the power of 27 bytes. So if we are having 2 to the power of 27 bytes and we know that this is a byte oriented protocol, means for every byte it allots the sequence number. So since we are having these number of bytes, what we can say, within 1 second we can generate 2 to the power of 27 sequence numbers we can generate, right? But according to the given question statement, the maximum segment lifetime is given 60 seconds. So if we are able to generate these number of sequence numbers within 1 second, then within that 60 seconds, means within that maximum segment lifetime, how many sequence numbers we can have? 60 into 2 to the power of 30 sequence numbers we have. 2 to the power of 27 number of sequence numbers we have. 2 to the power of 27 sequence numbers we have. Okay. Then the number of bits, therefore the number of bits in the frame sequence number field is equals to number of bits in frame sequence number field is equals to log of 60 into 2 to the power of 27 base 2. Okay, base 2. So then this I can write as log of 60 base 2 plus log of 2 to the power of 27 base 2. So now this I can write as 27, and log of 60 base 2, if you calculate this, you are going to get 5.9. So which is going to be 32.9. So 32.9 in the sense, closely you can have 33 bits. So the number of bits that should be part of the frame sequence number field should be 33 bits. So that 33 is the answer for this question. 33 is the answer for this question. So I hope you are clear with the explanation of this question. Let's move to next question. Look at this is the next question we have from computer network subject in GATE 2022 examination. Look at the question statement. Consider a 100 Mbps link between an earth station, that is sender, and a satellite, that is receiver, at an altitude of 2100 kilometers. The signal propagates at a speed of 3 into 10 power 8 meters per second. The time taken in milliseconds rounded off to the 2 decimal places for the receiver to completely receive a packet of 1000 bytes transmitted by the sender is. So look at here, who is the sender? Sender is something earth station, means something ground station. So I have some ground station here. Let's say this is my ground station. I have some ground station here, that is your sender. And I have receiver. What is the receiver here? Satellite. So this is my satellite. This is my satellite. Okay, this is my receiver now. Now, what is the question statement? It is mentioned that this satellite is having an altitude of 2100 kilometers, means D is given. D, what is the D value? 2100 kilometers. And the signal propagates at a speed of 3 into 10 power 8 meters per second. V is given. What is V? 3 into 10 power 8 meters per second. So when D and V are ready, we can calculate the TP. So that implies TP is equals to D by V. So what is the D? It is in terms of meters, this is in terms of kilometers. So converting this into meters. So 21 into 10 square into 10 power 3 by 3 into 10 power 5 into 10 power 3. So this 10 power 8 I am writing like this, 10 power 5 into 10 power 3. Okay. So now this is 10 power 2 plus 10 power 3, 10 power 5. So this is entirely cancelled. Then this 3 7 times. So means that the TP value we are getting as 7 milliseconds. Okay. Next. Bandwidth is given 100 Mbps. So what is the bandwidth here? 100 Mbps. The bandwidth is given as 100 Mbps. Okay. And it is saying that the packet size, what is the packet size here? 1000 bytes. 1000 bytes. So when L and B are ready, we can calculate the Tx. So Tx is equals to L by B. What is L? 1000 bytes. This is in terms of bytes, but this is in terms of bits. Converting these bytes into bits. So 8 into 10 power 3 by bandwidth 100 Mbps, 10 square into 10 power 6, right. So then this I can write as 8 into 10 power 3 by 10 square into 10 power 3 into 10 power 3. So 10 power 3, 10 power 3 cancel. This is going to be 0.08 milliseconds, 0.08 milliseconds. Right. So now understand the question statement here. The time taken for the receiver, who is the receiver? Satellite. The time taken for the receiver to completely receive a packet, of 1000 bytes transmitted by the sender. So means that first the sender has to place the message onto the channel. For that it is taking Tx time. And this message needs to be propagated to the receiver. For that it takes TP time. So it means that the time taken for the receiver to completely receive the packet of 1000 bytes transmitted by the sender is Tx plus Tp. What is the Tx value? 7 milliseconds. And what is the Tp value? 0.08 milliseconds. So total it is going to be 7.08 milliseconds. So 7.08 milliseconds is the answer for this question. Okay. So I believe you are clear with the explanation of this question. Let's move to next question. So now there is we are having this next question from the computer networks in GATE 2022 examination, which is based on DNS. Look at the question statement. Consider the resolution of the domain name www.gate.org.in by DNS resolver. Assume that no resource records are cached anywhere across the DNS server, and that iterative query mechanism is used in the resolution. The number of DNS query response pairs involved in completely resolving the domain name is. So here the first highlight point is we are using iterative mechanism, iterative query mechanism, okay. And what is the URL it is given? www.get.org.in. This is the URL address it is given, right. So now look at, so we all know that we have a DNS client like this. Let's suppose this is the DNS client, this is the DNS client, okay. This is the DNS client. So this DNS client wants to access this particular URL address. So when it wants to access this URL address, it sends a request to the local server. So this is the local DNS server. So this is the local DNS server. So this local DNS server, okay. So after receiving this request, what is it? DNS query request here? www.get.org.in. So this is the URL address which is being sent to local DNS server, okay. So this local DNS server, if it has the IP address of this URL address, it gives the response. But it is clearly mentioned that assume that no resource records are cached anywhere across the DNS servers. So it means that this particular URL address corresponding reference address is not part of this local DNS server. Then what this local DNS server will do? This local DNS server will forward the same URL address, to root DNS server. So this is your root DNS server, root level DNS server, root level DNS server. To this it forwards. So this is, so what it is forwarding here? The URL request www.get.org.in. This is being sent to root level DNS server. But this root DNS server does not have the IP address of this particular URL address. Then what it will do? This root DNS server can send, the reference address of TLD server. So what is the TLD server here? Let's say .in TLD server it gives. So .in TLD server, you can say that TLD server is one of the classification of TLD server is country TLD server, generic TLD servers. Like this, we are having some classifications of TLD servers. So this is the country TLD server. It forwards this request. It gives the reference address of country TLD server. .in TLD server address, reference address can be given by this root DNS server to the local DNS server. So now this local DNS server will forward this URL request. What is that URL request? www.get.org.in. So to this it forwards. So now after getting the reference address of this TLD server address, .in TLD server address, to that .in TLD server DNS server, this request can be forwarded by the local DNS server, okay. So now this is your .in TLD server, country top level domain server, you can say. So now this .in TLD server will give the reference address of SLD server, or else you can say that the second level TLD server. What is the second level TLD server? .org is also generic. It is a country, this portion is country TLD server, and this is, you can say that .org comes under generic TLD server. So you can call it as secondary TLD server. So that secondary TLD server, which means the .org TLD server reference address can be given by .org TLD server address can be given by okay, so can be given by this .in TLD server to the local DNS server. So now this local DNS server will forward the same www.get.org.in request, URL request to this .org TLD server. So now this is my .org TLD server. So to this .org TLD server, this particular URL address is being forwarded by local DNS server. So then this .org TLD server does not have the IP address of this URL address, but it has the authoritative reference address. So now it is providing authoritative server address. It is providing the authoritative server address. It is giving authoritative server address. Okay. So then look at. So now this particular address can be forwarded by this local DNS server. After getting the authoritative server address, this local DNS server will forward the same www.get.org.in. The same one will be forwarded to the next server, which is called authoritative server. So this is your authoritative server. So now this authoritative server, so whatever the URL address whatever the URL address we are having, all those URL addresses gets registered with this authoritative server. So obviously this authoritative server can have the IP address of this particular URL address. So now it gives the URL address, IP address of this particular URL address. So now this IP address, once it gets, then this local DNS server will respond to the DNS client with that same IP address. So then this DNS client is able to access this www.get.org.in URL address, right? So overall, it is asking about, as it is mentioned, iterative query mechanism, and it is asking about the number of DNS query response pairs. Number of DNS query response pairs we need to calculate. See, the interaction between this DNS client and local DNS server, this particular one is called as recursive. This is called recursive DNS query mechanism. This is called recursive DNS query mechanism. But when it comes to this side, now the interaction between this local DNS server and the rest of all servers, whatever the interaction that is happening, this interaction is said to be iterative. This is said to be iterative DNS query mechanism. Iterative DNS query mechanism. So, as the question is asking about iterative query mechanism and the DNS query response pairs, look at how many DNS query response pairs we have. This is collectively one pair here. This is collectively one pair. So the interaction between the local server and the root server, this is one pair. And the interaction between local DNS server and the .in server, this is one pair. And the interaction between the local DNS server and the second level TLD server is another pair, right? So this is second pair and this is the third pair. And the interaction between the local DNS server and the authoritative server is another pair here. So total, how many number of DNS query response pairs are being there? Total 4. So as it is iterative mechanism, so total you are having 4 number of DNS query response pairs are there. Okay. So the answer for this question is 4. So I hope you are clear with the explanation of this question. Thank you. So now we are going to see the next question as part of GET 2022 examination from computer networks. Look at this question statement. Consider a new block with 3 routers P, Q and R shown in the figure below. All the links have cost of unity. So the routers exchange the distance vector routing information and have converged on the routing tables, after which the link is QR fails. Assume that P and Q send out routing updates at random times, each at the same average rate. The probability of a routing loop information rounded off to 1 decimal place between P and Q leading to counting infinity problem is dash. So here if you consider this network, so let's say I am having router P here, router Q here and router R here. So it is mentioned that the cost is unit. So then what is the routing table of this P? If you consider the routing table of P, Q tends to 1 and R tends to 2, right? And then coming to this Q, and this is via Q. Next, this is having P tends to 1 and Q tends to R tends to 1, right? So it means that from Q to P it is 1, from Q to R it is 1. Here from P to Q it is 1, from P to R it is 2 via Q. And the same way coming to here, Q is 1 and P is 2. So these are the routing tables which we are having with respect to P, Q and R before the topological change. What is the topological change here? Q and R link is failed. Before this topological change, this is what the routing tables we are having. Now look at who is identifying this failure of this QR link? Q. So immediately this Q updates this R value as infinity, right? So after updating this R value as infinity, there are two possibilities here. So one possibility is if this Q has updated first to the Q, if the Q have updated, update first to the P, it means that if the Q sends the update to the P first. So what I am trying to say here is if Q sends update first to the P, if Q sends update first to the P, then what is the update it is sending? It is sending infinity. It is sending infinity. So you know that infinity, in distance vector routing protocol in connection with this quantity infinity, we are having one term like bad news and good news. What is the bad news? Increasing in the cost. What is the good news? Decreasing in the cost. Increasing in the cost, which is a bad news, that propagates slowly, but whereas decreasing in the cost is a good news which propagates faster. So now this Q is updating infinity. Infinity in the sense it is a bad news. Is it increment or decrement of the cost with respect to the R? It is increment. So increasing in the cost is a bad news. So bad news in the sense it propagates very slowly. After some amount of time, this Q, this P may get the information of this infinite, but there is no looping there. But when it comes to, let's say if P is happening, so if Q sends update first to the P, then we don't have looping, no looping. No looping is result here, right? Because of course this is going slowly, at the end reaching to the P, so that there is no loop. P is knowing about, without having any loop, P is knowing about that particular link. But for example, if P sends update, first to the Q, if P sends the update first to the Q, okay, so it means that this P is sending an update to the Q, like I am having a cost of 2 with respect to this R. So when it is sending this R to the Q, okay, so when this P have sent, so now look at, this is the P and this is the Q and this is the R, right? This is failed. Now this P is sending, I have a cost about R as 2, this is sending, and whenever it receives this, then this Q saved it as 3, right? It saved it as 3. So then this 3 may send again, this Q can send this 3 to the P. Then this P may update it as Q, this P may update it as 4. So then it may send 4 to the Q, then this Q can send 4 to the P, then this P can save it as 5. Then it sends 5. Then it can save it as 6 and it can send the 6 to the P. So this is the way between these P and Q, there is a possibility for looping here. Right? So that is happening when the P is updated first. If the P updates first to the Q, then only looping. But if the Q updates first to the P, then there is no looping. So if P sends update first to the Q, then looping can be possible, right? So then looping can be possible. Looping is possible. But here there is no looping. So among these two possibilities, only one possibility is leading to looping problem. So hence the probability of routing loop formation between P and Q leading to counter infinity problem is 0.5. So 0.5 is the answer for this question. Okay. So I believe you are clear with the explanation of this.